Go live. Hi everyone, welcome to another episode of Science and Technology Q&A for kids and others. And I see that we have a bunch of questions left over from last week. Let's see, we have one question from Ettore here. Any tips on how to make nice presentations? You know, I've been making presentations a really weird way for a really long time, which is that I do live coding. And that's really something made possible by our whole Wolfram language technology stack, because I can like type a small amount of code in and have something interesting happen. And I guess I know our language well enough that there's a decent chance the code I type in will actually work. I think that from what I can tell, that's a very effective way to make presentations, because people can then actually take away something practical, which is they could type this code in too. And usually when I do a presentation in modern times, I'll create a Wolfram notebook which is mixture of code, and it's generating all kinds of pictures, and maybe I'll type a little bit of text in, but mostly it'll be code generating pictures. And then I'll say publish to cloud, and I'll get a version of that notebook that's been put in the cloud. And you even nowadays get this little QR code that people can scan if it was an in-person event, that they can then get immediate access to that notebook. So it's like you've got the notes from the talk in not just the static notes, but also something where you can go in and start changing the code and so on. You can do that from a phone or from a computer or whatever else. So that's kind of an interesting mechanism for making presentations. I would say that for me, I suppose I should admit a few things about presentations that I make. One thing that is always bad for me, if I prepare too long in advance, it will be a worse presentation. Now, I must have given thousands and thousands of presentations in my time. So I have a decent amount of experience. But what I found is, if I I'm going to prepare this 3 days in advance, et cetera, et cetera, et cetera, by the time I actually get to give the presentation, I'm not in the same mood as when I prepared it. I am like, oh, what did I mean by this note that I made? What was I talking about? And it's very, it doesn't flow very well. Whereas if I'm like, I think about what I'm going to do just before I give the presentation, I'm kind of in the same mood and I'm ready, and I'm kind of, and I'm kind of all thinking about it and so on, and then it works much better. I mean, for me, one of the issues is if I'm, the more I know the audience, the more I understand something about the audience, the better a presentation I'm going to be able to make. And there have been a few times, I always keep track of the times when it's just been, as far as I'm concerned, an utter disaster. Like, presentations I prepared, and then like if it's an in-person event, I remember one from many years ago now, in-person event where I'm physically there and I'm meeting a bunch of the audience, and the night before or something, some grand sort of keynote thing or some such other thing, and I'm like, oh my gosh, this is the wrong talk for this audience. But I prepared the whole thing. And so it's like, well, I guess I get to give it. And yeah, it was the wrong talk for that audience. And I think that so I think that's a relevant thing. I think that for me, it's always, I guess I do best when I'm not when I'm not saying the exact same thing I've said a bunch of times before. Now, having said that, I've ended up talking about, so there's some topics that I've ended up talking about over and over and over again, because it's like they're important. It's always fun to see people, understand them for the first time. And I think it is the case that one gets a little bit better at explaining the same thing over again. A thing that I've done in terms of giving presentations, you're asking this question, so I'll try and give an answer. I mean, I'm really not, I've actually never used PowerPoint, for example. I sometimes use our presentation system in Wolfram notebooks, where you can, interact with the presentation as well as just put up a slide. But this idea where I put, where people put a certain amount of text from what they're going to say up on the screen for people to see. I've never done that. I don't know. I'm not sure it's necessarily a bad thing, but maybe I haven't prepared enough in advance what precisely I'm going to say to be able to do that. A thing that I also tend to do is I tend to have a slide picker. Usually, I'm using multiple screens, and even when I'm doing an in-person talk, I'll have two screens. So one is a slide picker, and one is what I'm actually showing and potentially typing live code into when I'm giving the presentation. And so what will typically happen is I'll have a slide picker where I have a bunch of collections of they're usually notebooks where I'm clicking a particular slide, and as I go through the talk I'm giving, I haven't necessarily arranged those slides in order beforehand. I'm just picking them out in real time from these sort of slide pickers. And that means that if I decide to change the order in which I do things in the talk, it's okay, because I'm just picking out a different thing. And then when it comes to Q&A, then it's great, because it's like somebody asks a question and oh yeah, I've got a slide here, boom, here it is up on the screen. And that works really well. Now, a few times when I've been giving, I always find it much more difficult to give short talks than long talks. Maybe people who have been coming to these live streams can recognize the reasons for that. I find it much easier to kind of explain things long form than I do to say, oh yeah, compress it into 2 sentences, what's the sound bite, so to speak. But there's some times when I've been, sometimes somewhat reluctantly, agreed to give sort of the short, the 18-minute talk or whatever, and where I'm like, I've got to compress a whole bunch of stuff into this fairly short amount of time. And what I've ended up doing in those cases, I have to say, I haven't done one of those for a while, but I end up writing out every single word I'm going to say. And what I found is, I guess that I've learned to write more or less as I talk. And so it's, when I'm ending up essentially reading something that I wrote word for word, it's okay. It works. It doesn't sound like, oh, you're just reading from a script and it's really boring, because I managed to write it as I would say it anyway, and then it still seems perfectly possible to present it as you would have been thinking it when you wrote it. So anyway, a few comments on, but I think the thing for me that has been doing kind of live coding, live programming, to me, that's the most engaged and energetic thing, because it's like you're figuring stuff out in real time along with the audience. If you get feedback, the feedback is always great, then it's kind of like you can adjust accordingly, and that to me generates kind of a good interaction with the audience. I mean, the other thing that's always an issue is, how do you start? Because it's like, even if you just know the first 3 sentences you're going to say, more or less, that really helps a lot often. If you're like, here's this audience, and it's like, I really didn't think about anything I was going to say. For me at least, once I'm sort of off and running and I've got some kind of approach, some kind of way that I'm dealing with this particular audience, it's then one's off and running and one's in good shape. But if one thinks, so for example, for me, I'll give talks that are to very technical audiences. I'll give talks that are to more to what this is intended for, kids and so on. So I'm not sure if you're doing. I mean, the other thing that happens is, so okay, the other question for people is, well, what if you just you're really terrified of giving some talk in front of a bunch of people? That's not really been my problem ever. In fact, I think one time years ago, when I first had these biometric devices that would measure heart rate and so on, I thought, am I going to do this? I'm going to show off some biometric device, and I'm going to see whether, when I'm in front of a big audience, whether my heart rate actually goes up. And well, the answer was it didn't. So it was, for whatever reason, but I think the point is that somehow there comes a point where you're just like, I see people who do great in one-on-one interactions, and then we put them in front of an audience, they kind of freeze. There are also people who do well in front of an audience, but one-on-one, they're very kind of, they don't interact very well. I think that in terms of people where it's like, oh my gosh, I'm going to be in front of this big audience and everybody's going to notice what I'm doing. It's like, I don't know. I think sometimes people kind of overthink what's going to happen, and they kind of sometimes over prepare, and that means that they end up being sort of, they over prepare the fact that they're nervous about giving the talk, and the whole thing doesn't, it would do better if they just were able to kind of imagine they're talking to one person. Pick a person. Okay, you're talking to that person. The fact there's 1,000 other people there or 20 other people there or whatever is like, who cares? You're mostly having this conversation with this one person. I think that's a potential strategy. I don't know. It's not that, for me personally, that's not been such an issue. I mean, the thing that happens is that sometimes I'm like, oh my gosh, this is a talk that's going to be an absolute disaster, because I haven't really even thought about what I'm going to say. I don't really understand the audience, et cetera, et cetera, et cetera. And then when it gets started, there's enough kind of energy and enough interaction with the audience, enough positive feedback or something, it goes really, really well. And sometimes it'll be like you're going to, you think that, oh yeah, this is easy, I understand this audience, et cetera, et cetera, et cetera. And it's like, nobody's responding. I'm sort of telling a joke and nobody's responding to that. And, and it gets to be very negative feedback. Anyway, a few 2 cents worth. I mean, to tell a couple of little minor stories. I mean, the other thing, one's doing live coding kinds of presentations to audiences, obviously you have to have a computer and a computer projector and all that kind of thing. It's got to actually work. And it's always bizarre to me that I've given talks in just a huge collection of different venues around the world over the course of, many decades now. But when I first started using computers with computer projectors and so on, that was probably in the 1980s. And that was very early. And when, computer projectors were these big clunky things, and they were really for projecting televisions, and computers weren't portable, and et cetera, et cetera, et cetera. And things were much more difficult. And all kinds of crazy things happened. And, but the thing that was most bizarre to me is in places where you thought this couldn't possibly work. There's no way. I remember being in Moscow, in Russia, sometime in, what was it? That must have been maybe 1991. And it's like, we got this projector and its diagnostic messages are in Russian. And, there were Russian-speaking people there, but it was a little bit, and, things were connected. There were connectors that were different and all this kind of thing. And it's like, this isn't ever going to work. And we had to borrow some computer and so on and so on and so on. Works fine. Then you're in a situation where it's like, this is the most, like for example, I gave a talk at TED once, which is some big fancy conference, and that has like the absolutely top of the line audio-visual setup. And fortunately, it was, I was like, well, let's just test this, a few hours before. And it's like, oh my gosh, this doesn't work. And, they have the most high-end thing where they've got a whole bank of equipment and, people and giant, incredibly high resolution projectors and so on. And oh my gosh, it doesn't work. Well, I learned something there, which was a very bizarre fact, which is the way that a computer sends its data to a projector or to an external display. It has to kind of negotiate. The computer may have a certain resolution to its display. For example, a computer might have 2,000 pixels across the screen, and the projector might be might only allow 1,500 pixels across its, when it projects it. So the question is, can the projector sort of tell the computer, please only send me 1,500 pixels across? Because if you have 2,000 pixels across the computer screen, if you just say, well, send me the first 1,500 pixels, well, then you don't see the whole display. If you say, send me the whole thing, well, it's a little bit tricky because you've got to take what was, let's say, 4 pixels on the computer screen and turn that into 3 pixels for the projector. And you've got to figure out if it was, red, red, green, blue were the pixels on the computer screen. how does that translate to the pixels on the projector and so on? So it's a bit tricky. And there's a whole elaborate kind of, underworld or something of how computers and projectors and so on communicate, something called ETI, which is some mechanism for, EA, am I remembering that correctly? I'm not sure I'm remembering that correctly. There's an acronym. I think I got the right one, but I might not have done, for how the computer sends back information. And in this particular case, the fancy audiovisual system was sending back kind of fake information to the computer that was totally confusing the computer, causing it to send completely the wrong data. The whole fancy audiovisual system was not working as a result. And it required having a weird little box that was connected between the computer and the other stuff that was kind of refaking the signal that had to be sent. But so that's one of the weird things that happens doing these things in person. All right. Well, let's see. There's a completely different question here from Pax. Why are there so many concepts in mathematics that are not realized in the physical world? Actually, one of the big surprises is that a lot of the mathematics that has been invented has actually ended up being sometimes invented, but then 50 years, 100 years later, it ends up being used to describe physics. So just to review a little bit of the history of mathematics and physics and so on, I mean, in the kind of mathematics kind of originated, mathematics as we know it sort of originated in Babylonian times, maybe 3,000 years ago. And really there were two branches of mathematics, arithmetic and geometry. Arithmetic was mostly used for dealing with things to do with money and amounts of money and so on. Geometry used for surveying land and deciding, what was the area of the land that you owned and things like this. Well, at the time, it wasn't obvious whether kind of these mathematical ideas applied to physics, so to speak. Physics in those days, the most sort of important physics was looking at planets and so on, and looking at things in the sky. And it probably didn't hurt that there wasn't electric light, obviously, in those days. And so the sky at night was probably it was nice and bright, and people really noticed, oh, there's this extra star-like thing that's moving across the sky. Oh, it's a moving star. Well, okay, then we know now that's a planet. And in those days, people had names for these things. They didn't really quite know all the details of what they were, and that they were things like the Earth and so on. And they tried to make kind of models for where would Mars be, where would Jupiter be. They knew about Mars, Jupiter, Saturn. That was as far as they knew. They knew about Venus and Mercury also. But where would those? I think they knew about Mercury. Yes, they will have known about Mercury. Where will those things be? Like, a week from now, a month from now, a year from now, where will Jupiter be in the sky? And in fact, one of the things that the Babylonians did is they kept very good records. So they had astronomical diaries that they wrote every single day for 700 years. And in fact, those diaries give us some of the best information we have on things like when eclipses happened and things which allow us to, even today, understand things about the motion of the Earth and so on that we can't get from making measurements over shorter periods of time. But in any case, they wanted to figure out, okay, where's Jupiter going to be, some number of years from now? And by the way, I mean, a lot of things that they discovered were things like, 19-year cycles, like the cycle for tides and eclipses and so on. That's 19 and something years long. It's rather impressive that any civilization, group, whatever, kind of been keeping records as consistently as that they could really find a 19-year cycle in something. It's sort of a remarkable thing that, every day for 700 years, and we have about 1 or 2% of that 700-year run still exists on tablets and so on in museums around the world. And it's sort of gradually been pieced together. But in any case, so they were interested in where's Jupiter going to be, and so they tried to work out. They tried to use math to figure that out, and they said, well, there's this curve, and it goes up, and it goes up, and it goes up. They actually had a little bit of ability to sort of, in a sense, plot things like we do with plotting curves and so on. And they were like, okay, this curve is going like that. It's going to go to this place at this time. And that was the beginning of sort of the effort to, use math for physics, for science, was at that time. And they did rather well. And then later on, there were sort of more elaborate models that got developed, which again used math. In those days, for example, there were problems like that there wasn't really a mathematical notation that existed. People had to describe their math in words. There is this circle, and next to the circle there's this other one, et cetera, et cetera, et cetera. And there's this thing that increases in proportion to this and that and the other. It was all just words. The idea of notation for math didn't really come in until much later, more like the 1400s and so on. So that was kind of an impediment. Actually, in some of the early work that was done, even people like Kepler in the early 1600s was still doing things like using music notation, because music notation of where notes get placed on a stave and so on, that was introduced around 1000 AD. And that was actually used as sort of notation by Kepler, because he didn't really have math notation for certain kinds of things. But, by the time that the big sort of explosion of you can use math to do science was in the late 1600s, with people, well, first Galileo and then Newton, basically realizing that there were sort of mathematical calculations that would allow you to explain things about physics. And in particular, Newton ended up inventing calculus as a way to explain the motion of not just planets, but also comets, which have these elliptical trajectories and so on. That was kind of the big thing. And so the methods of mathematics that were, in that case, calculus was sort of invented in the service of physics. What had existed at the time was geometry, a lot of geometry, a lot of things about properties of ellipses, properties of this, properties of that. If you look at the early works on astronomy by people like Ptolemy, Regiomontanus, people like that, you'll find that they're full of theorems that say things like there can only be at most, I forget how many it is, 3 eclipses in a given year. And their proof of that theorem is a bunch of pictures of triangles showing that, because the sun, the moon, the earth are arranged in this way, you can only arrange them that way, and it's a geometrical proof. So I suppose the first place where things were invented that were used later was back when Euclid, maybe 1st century BC or so, was doing was codifying geometry and putting together his collection of axioms and theorems about geometry. Most of the geometry that people learn in like high school and so on was known by Euclid and was written down by Euclid. Things like, I don't know, you draw in a circle, you draw, you have something on the diameter of the circle and you put lines up to meet on the circle. Oh, that angle is always 90 degrees. That was one of the fairly elementary results of Euclid. But so those results, sort of one of the first places where sort of math was invented. Math was not really used for a long time, and then math turned out to be useful, was in the use of geometry for doing astronomical calculations and astronomical sort of theorem proving. Another place where geometry showed up was in optics, figuring out if you have light rays and you have a lens, for example, and the light rays are going along and the lens makes the light rays converge, it bends the light rays, but through a certain angle, and there are all sorts of properties of, this angle is equal to that angle, and so on and so on and so on. And it becomes kind of like a standard high school geometry problem to figure out what's going to happen. So that was another use. But then what happened is through the 1600s, 1700s, even 1800s, most of the math that was done in the service of physics. So people invented these things called differential equations, which were kind of equations that say, if you change this, if this changes, that's how it changes the rate at which something else changes. Or if this changes at a certain rate, the rate at which something else changes is determined by that. It's an equation that says, as you change the size of this or the rate of that, then it changes the rate of this other thing in that way. So that was kind of the mathematical approach that was developed, particularly in the 1700s, early 1800s. That was kind of the big thing that was being developed in math. And that was the thing that was developed for doing physics. And first it was for things like fluid mechanics, the motion of water and air and so on. Then for things like electrodynamics, electromagnetic fields, things like that. They all sort of fitted into that kind of mathematical framework. The thing that happened in math in the 1800s was people started doing math that didn't immediately connect to the physical world. And so one of the first things there was one of the big results of Euclid, or big claims of Euclid, is parallel lines never cross. And so if you just draw parallel lines on a plane, they don't cross. If you draw parallel lines even on a sphere, they can cross. And one of the things that was sort of believed is that in actual space, as it exists in the universe, in physics, parallel lines never cross. Well, it turns out that isn't true, but the idea that you even should consider a mathematical setup where parallel lines could cross, you have a space where parallel lines can cross, that was an idea a chap called Lobachevsky in the 1830s, 40s, and so on, was really big on. That idea was an idea that was sort of imagined in math, but didn't really have a place in physics until Einstein came along and figured out our still, well, somewhat current theory of gravity around 1915, where that has the idea that space is actually curved, that the presence of mass produces curvature in space, which is what leads to gravity, and it leads parallel lines, as in you shoot two laser beams and they go in quotes lines, except you might think they were parallel, but actually the effect of gravity is to curve space and cause those parallel lines potentially to cross. So that was another place where sort of the ideas of Lobachevsky about curved space ended up, about 80 years later, becoming relevant to physics. Then there was an idea, a chap called Évariste Galois came up with this idea of group theory, which has to do with sort of abstractly figuring out if you have, let's say, an object, I don't know, a tetrahedron or something, and you say, what are the possible things you can do to the tetrahedron? Or take a Rubik's Cube, for example. What are the possible motions of a Rubik's Cube? And if you twist one side 4 times, you'll get back to what you started from. If you twist several different things in different ways, it will take you a lot longer to get back to what you started from. And there's a kind of way of writing down sort of an algebra of, if you have this particular move that you make on the Rubik's Cube and you combine it with this move, and you combine it with that move, how is that equivalent to some other set of moves you could do? Or how does that set of moves eventually come back to the Rubik's Cube all being put back together again, and so on? And that idea of sort of thinking about the sort of abstract notion of this sort of algebra of things you can do, that idea of group theory that originated in the 1830s or so. And again, it was something which at the beginning was a purely mathematical interest. It was invented for understanding things about equations of the 5th degree, equations that involve, quadratic equations like x squared and so on, x to the 5th and so on. There was a whole question about whether you could solve those equations in terms of cube roots and square roots and so on. And this was a proof that you couldn't, and that came from this sort of abstract area of group theory. So for a long time, it's like group theory is nice and group theory is in math, but group theory isn't relevant to physics. By the time, by particularly the 1950s and 1960s, but even there have been other work earlier than that, turns out group theory is super relevant to understand things about, well, first atoms, and then things about particles and quarks and so on. And actually group theory is a big part of the story of how kind of the modern conception of physics is put together. So again, a span of something like 100 or so years between when it was sort of invented as a math idea and when it ended up getting applied in physics. Now, there are other kinds of things that got invented. By the late 1800s, people were very big on this idea of, let's just imagine a kind of a formal system, something that you could just sort of write down and do manipulations and calculations with, even though it has nothing to do with anything we know about in the real world. And so, for example, one thing that was invented at that time by a chap called Georg Cantor was transfinite numbers, which are kind of like, they're different shades of infinity. You might say, oh, we've got an infinite number. It's just infinity. There's just, a thing called infinity. Well, he had this idea of transfinite numbers, where there's just an infinite number of different variations of infinity. You can have sort of infinity plus 1, infinity to the power infinity, and so on. And there's a way of distinguishing these things. And so there's this whole sort of world of transfinite numbers. So that's an example of something that was invented in the 1880s or so, and still today doesn't really have a physics application. Actually, in our physics project, I think there is some slight sign that we will need to use ideas from transfinite numbers. But mostly, that's an example of a piece of math that sort of got, in a sense, overbuilt and wasn't relevant to physics. In other places, there's it's sort of interesting, because my basic point of view is whenever you have sort of an elegant enough way of thinking about things, there will be a way to apply it. But somehow part of that is what you choose to study as much as how you choose to study it. So for example, there are plenty of phenomena in physics where you just say, that's really complicated, we don't know how that works. Even though we might know how to sort of break it down into small pieces and know how the small pieces work, we don't know how to build it up again. That's true in, for example, fluid turbulence. When you see sort of water flowing quickly in a waterfall or something like that, you see all of this, bubbling around water and so on. It's very complicated. We still don't really know how that works, even though we know perfectly well how the underlying physics of water works. And so in cases like that, there's sort of a question of, well, what do you choose to study? There are questions about the waterfall that we can study using certain kinds of mathematical methods, and then we can say, great, that those mathematical methods worked. But there are other kinds of things that we don't manage to study, and there we can't really there's a sort of question. Once we've invented a mathematical method, usually we can find a thing to study for which that mathematical method works, so long as the mathematical method is somehow elegant enough. And I've certainly noticed that I made up a bunch of models of sort of computational models of things. And when the models are very clean and very simple, they always get applications. When the models are these very complicated things that are very specially constructed, well, then maybe they're of interest for studying the model itself, but they're not of interest for studying sort of the physical world. So I think that's it's kind of the and I mean, when you say that many concepts in mathematics are not realized in physics, I think that the vast majority have in fact ended up getting realized in physics, partly because of the choice of what we study in physics. I think in our physics project recently, a whole kind of boatload of new sort of advanced mathematical ideas that have been floating around for 100 years or more, that particularly ideas about and from mathematical logic that have seemed like they're just like, oh, well, that's interesting for studying mathematical logic and the foundations of mathematics, but why would we care about that in physics? Now it's incredibly relevant. There are notions, I think, called the Church-Rosser property, which is has been kind of an obscure property in mathematical logic, is the reason that relativity works in the physical world in our models. So these things which were kind of obscure pieces of mathematical logic end up becoming applied to physics. And it's an interesting phenomenon. Anyway, there's probably more to say about that. I think we've got a lot of other questions here. So let me try and get to a few of these others. Oh boy, there's a question here. What cryptocurrencies am I a fan of? Do you think any of them will win big in 2021? That's more of a, I think maybe I should explain for people's benefit what cryptocurrencies are. So the most famous cryptocurrency is Bitcoin. That's been the most valuable cryptocurrency. I think it's like, these days, what was it? It's like $500 billion is the value of all of the Bitcoin that exists today. And that's a big number, because that's comparable to, it's half the size of the very biggest companies and their values and so on. So, okay, a little bit of an explanation. What is Bitcoin? What are cryptocurrencies? What's the idea? So I guess the big thing to start from is the idea of blockchain, which is kind of the underlying technology of cryptocurrencies. And here's the basic point. So there's a question of, if you do financial transactions, if you say so-and-so is going to own this piece of land, et cetera, et cetera, et cetera, you want to make a ledger of what happened. You want to somehow have a record of, oh, this person owns this piece of land. This person owns this number of dollars. This person paid this number of dollars to this person, and so on. You want to have some kind of, ledger of what happened, so that you can say, this is really how things are in the world. So-and-so paid so-and-so $1,000, and now the new person has that $1,000 and the old person doesn't have that $1,000. And you want there to be no doubt about that. You want it to be the case that there's a sort of a information about that. So in the world in general, you know, when you have a bank account or something, I mean, there was a time 100 years, 150 years ago or something, when if you deposited money in the bank, there was a vault underneath the bank and your money got put in that vault, at least in a first approximation. Then things got much more complicated and banks started lending out money to other people, and their whole elaborate system of modern banking got started. But in some first approximation, you could imagine, you know, you put your money in a bank, the thing is just sitting there in, you know, in a vault underneath the bank. But in modern times, that's absolutely not how it works. And instead, it's just an electronic record that, yes, you own this money, and when you pay the money to somebody else, then they get it, and you don't have it anymore. So the idea of blockchain is, the question is, who maintains that ledger? So for example, typically, if you buy a piece of real estate, you say, I'm buying this house. The question is, how does anybody know that you own that house? Well, the answer is, there's a registry, a central registry, a registry of deeds, a title registry. And somewhere you can go to your local town, whatever, and there will be a piece of paper that says you own this piece of land, and that piece of paper is kind of securely kept by your town or whatever else. And if somebody says, no, I own it, you go to the title registry and you can say, no, it's not true. Here's the piece of paper that proves I own it. Okay, so the issue is, how do you get, what's a kind of a way to do that? So one way to do it is you just have one centralized place. Now, let's imagine you had 2 title registries. There'd be a problem, or 3 title registries. And each one has pieces of paper that says, this person owns this piece of land, this person owns this piece of land. Well, what happens if the pieces of paper in the different title registries disagree? If 2 titles registry say, you know, Jane owns this piece of land, and 1 title registry says Amy owns this piece of land, what happens then? Well, so that's why in most traditional sort of ledgers, there's only 1 copy, because there's 1 definitive version of you know, who owns the thing. So what happens with blockchain, that the sort of the big idea of blockchain is to have a distributed ledger, to have it be the case that you can have thousands of copies of the ledger, and that are distributed on different computers around the world, but that all have the property that they all somehow are made to agree. Okay, so it's a pretty clever system that's kind of elaborate, that basically is a system of incentives that causes people to want those ledgers to all agree. And the idea in Bitcoin, for example, is, here's the idea. The idea is that what's going to happen is, on this blockchain, there are these blocks, and a block contains, let's say, 1,000 transactions. Doesn't matter what the number is. Let's say 100, 1,000, doesn't matter how many transactions. And that, what's going to happen is, at some point, that block is going to be on the blockchain. It's going to be part of the ledger, and everybody's going to agree that that block is correct. And so every so often, you want to put a block on the blockchain that contains some bucket of transactions, and everybody's going to confirm that, yes, that block is correct. And so it's going to become part of the ledger, shared across, you know, 5,000 machines, 10,000 machines, whatever it is around the world that are running Bitcoin blockchain servers and so on. So the question then is, how do you get everybody to the point where they agree that what's in that block is correct? So first question is, if you're doing a transaction, if you want to, so what's in the block? What's in the block is a bunch of records that say A paid B some number of Bitcoins, and or some number of Satoshi, which is 100 millionth of a Bitcoin. You know, so somebody paid something, and you're recording, and you want to record that in this ledger. And then if you want to know, well, how much Bitcoin do you have? You can just go back in this ledger and you can say, well, I started with this amount, and then I paid this person this person paid me this, et cetera, et cetera, et cetera. You can figure out how much do you now have. And because this ledger is something that everybody has agreed to, everybody will agree about how much Bitcoin I have. Okay, so the question then is, so I want to make a transaction. And what I would do then is I'd say, okay, I'm going to make this transaction. I have to prove that I'm allowed to make this transaction. and then I have to sort of submit this transaction, and people have to decide whether they should add it to these blocks that are being added to the blockchain ledger. This is a little complicated. I can probably explain how this works. Okay, so the question is, well, let me say roughly how it works and then maybe go through more details. There's this very bizarre idea of so-called mining of Bitcoin. And actually, I happen to think that this idea actually came from some science that I did in the early 1980s. And I think the person who invented Bitcoin, and that's sort of an anonymous thing, nobody really officially knows who that was. But I have pretty sure that a bunch of things that I figured out about science to do with this phenomenon of computational irreducibility turned into this incredibly bizarre thing that I'm about to describe that's called proof of work for Bitcoin. And so the question is, who gets to say that they made up the contents for a block in the Bitcoin blockchain? You know, of the maybe 5,000 people who are running Bitcoin servers around the world, who are going to get copies of the Bitcoin blockchain, who gets to be the one who says, I made up this block? Well, that's determined by who has, again, I'm skipping a bunch of stuff because there's a whole depth of description here about how the cryptography works in these things. But roughly, it's what has to happen is, if you solve this particular computational problem, it's kind of a pointless, silly computational problem that says basically a thing that usually is used for taking, for example, a message and generating a so-called hash code. You're saying, given this message, I'm going to figure out what's a 10-digit number that is a good sort of short description of this message. And if I change the message, I want to change that 10-digit number most of the time, although there'll be some messages that end up with the same 10-digit number just because there isn't as much information in a 10-digit number as there is in your whole message. Well, so the idea is, can you find a message which will produce a particular hash code, or a hash code which ends in some number of zeros? And that's a bizarre kind of pointless problem. But it's also a problem it seems to be a sort of computationally irreducible problem. It seems to be something where you have to do a certain amount of computational work in order to answer that question. And so the idea is that you can have different computers around the world, different people around the world who are all sort of competing to find that, to sort of solve that computational problem and be the one who says, yes, I'm the one who figured this out first. I'm going to get to put the next block on the Bitcoin blockchain. And it's kind of a weird thing because that process of trying to solve that computational problem just takes a lot of computational effort. And so people build all kinds of special purpose computers that are specially set up to be really fast at doing, giga hashes per second, 1 billion hashes per second to try and find these answers. And, people spend lots of electrical power running those computers, and it's all a kind of very weird setup. That and certainly I couldn't have imagined when I came up with this idea of computational irreducibility that it would be used for this very bizarre purpose. But it's kind of like when you think about money where gold is sort of the thing that's backing the money. It's like one of the things that depends on is gold is hard to mine. It's hard to find the gold. It's hard to get it out of the ground and so on. It's and that's why you can sort of justify saying gold is valuable. It's the same kind of thing with Bitcoin mining. But anyway, so then you're kind of you're taking so essentially there are the Bitcoin miners can say, yes, I got this thing first, so I'm the one who gets to add this block. And one of the things that happens is everybody who wants their transaction included in that block, included in that piece of the ledger, they pay a small commission. They pay some number of cents or 10 cents, whatever it is, 1 cent. They pay that to be able to get their transaction included in the Bitcoin blockchain ledger. Okay, so then the person who mines, who gets to be the person who creates that block, picks up all those commissions. They get to take all those commissions that people are paying. They get those commissions. So it's worth doing this kind of mining of Bitcoin to get those commissions and so on. Now, I'm simplifying a bit how this works, but basically what's happening is somebody says, yes, I've got this block, and other people will then confirm that block. And gradually, people will have gotten to the point where they say, yes, it's going to get copied onto all those 4,000 machines. And there's usually on Bitcoin, there's a block mined about every 10 minutes. And usually it takes about 24 hours before people are like absolutely certain that this block is not going to get reversed. Nobody's going to say, oh, there's more people who say this is the correct block than that's the correct block. But okay, so what's the point of all of this and how does it all work? It's really a very weird thing because in a sense, Bitcoin is valuable because people think it's valuable. People have put money into it, $500 billion into it, and they think, well, actually they haven't put all that money in, but that's what they think it's worth. So if you say, I'm going to convert my Bitcoin to dollars, then I'm going to get a conversion that's based on the fact that all the Bitcoin in the world is worth $500 billion. And the question is, why is that the right number? Well, nobody really knows. It's like if people are prepared to pay it, then it's the right number. It's a very sort of flexible thing. And that means as people believe different things about Bitcoin and so on, it'll be, oh, it's more valuable today because more people are trying to buy it. Oh, it's less valuable, nobody cares about it, it's gone down in value. Or, some government outlawed it. Oh, it's going to go down in value because not as many people can hold it, or whatever else. Or people are worried about how existing currencies are unstable, so it's going to go up. It's much more volatile. It jumps around in value much more than most currencies and most countries jump around in value. But in any case, so the thing that Bitcoin mostly is a sort of repository of value. People put money into Bitcoin. Why? Well, because they hope that when it's in Bitcoin, it's going to go up in value and they're going to be able to sell it again and get more money back. They're kind of speculating on what's going to happen in the value of Bitcoin. And that is the vast majority of what has been spent on what is in Bitcoin is people speculating on what's going to happen with Bitcoin. Now, you might say, well, can you actually use it to buy things? Well, at various times people have I remember there's one place in Palo Alto, California, where it's like a coffee shop type thing where you can buy your coffee for Bitcoin. I'm not sure that that's a very I've seen that only in one place. There are sometimes there are Bitcoin exchange machines where you can put cash in and get Bitcoin sent to your account. Those have existed. Those have sort of popped up in donut stores and things like that in different places. I don't know whether those are still going. And unfortunately, they often have these big signs on them saying, be careful, make sure that what you're doing with Bitcoin isn't a scam. Because it's something where people think Bitcoin is a very untrackable kind of thing. Now, it's a little weird that they think it's untrackable because in some sense, Bitcoin is the most trackable of anything because the ledger of all the transactions that happened is absolutely publicly available. The only thing that isn't publicly available is who is behind those transactions. Everybody gets kind of an ID, and you get these kind of weird long numbers that represent your account, represent who you are, and so on. And there isn't a connection between the who you are and who you actually are in real life, and that number that's associated with Bitcoin. But it's one of these things where in a sense it's a more open ledger of what's going on than anything else. It's just that final last step of who's the actual person behind this is not immediately known. But in any case, so people say, oh, this is an untrackable way of transferring money from this to that, and to some extent that's true. And governments get very concerned about, oh, what if everybody moved their money into Bitcoin and then avoided paying taxes, or moved their money to another country, moved their money out of our country, so nobody's buying, nobody has Venezuelan currency anymore because it all turned into Bitcoin or something. And at times, various governments have considered making some kind of digital currency making some kind of thing like Bitcoin be the currency for their country, or even making Bitcoin be the currency for their country. That hasn't happened yet, at least. And there are a bunch of reasons why that probably isn't a very good idea. But in any case, so the main thing that's going on with Bitcoin is people speculating on whether the value of Bitcoin is going to go up. The actual buying of things with Bitcoin, not very much of that. Another bizarre thing is so-called ICOs, initial coin offerings, where people are inventing new cryptocurrencies and are selling people initial kind of shares in that new cryptocurrency in another existing cryptocurrency like Bitcoin. So a bunch of the kind of the sort of transactions that happen on Bitcoin are for ICOs, for people buying other new cryptocurrencies. So Bitcoin is mostly, so there are these different cryptocurrencies. Bitcoin is the biggest. The second biggest is one called Ethereum, and then there are a whole sequence of other ones. And we've worked with a lot of these companies, so I know lots about a bunch of these cryptocurrencies. These, I shouldn't say companies, because they're often very weird organizations that are sort of combination foundations, non-profits, this, that, companies, et cetera, et cetera, et cetera. They're sort of weird kinds of constructions. But one of the big ideas that sort of originated with Ethereum is this idea of smart contracts, which is the idea that not only can you have transactions that where you have sort of this person paid this person this amount in this cryptocurrency, you can also have sort of things that have more logic to them that depend on other things. And for example, one thing you can do is you can have a contract that says just, I own this thing. And so on Ethereum for a long time, the favorite thing to own was CryptoKitties, which are, what are they? They are completely virtual things. And they're these cool looking pictures of cats, and people can say, I own this CryptoKitty. And you can prove you own it because there's this smart contract on Ethereum that says that you own this CryptoKitty, and it's on the Ethereum blockchain ledger. And so it sort of proves you really own this CryptoKitty. And then you can say, well, I own this CryptoKitty, but I'm prepared to sell you this CryptoKitty. And eventually you build up a market in CryptoKitties, and you can use that. And then so you're essentially building value in CryptoKitties, even though what is this CryptoKitty? It is simply your right to have, it is simply the fact that you have this weird looking cat that has these particular characteristics. Now, in the real world, there are plenty of markets where people are buying things where it's pretty virtualized like that. I mean, it's also true in computer games and video games that people also have virtual goods there, which they're buying and selling. And to some extent, that's merged with the idea of buying and selling things in cryptocurrencies, although not as much as one might have expected. But in any case, so the question that was asked is, what are the new and exciting cryptocurrencies that and what will happen to cryptocurrencies? And I think that what will happen to cryptocurrencies is a complicated question about the economics of the world that I don't think I have any great insight about. And what will happen to these various stimuluses that governments are putting into their economies to which in some cases amount to sort of printing money to give everybody a check for X number of dollars or something. How will that affect the value of dollars altogether? How will that compare to people deciding to put their money into Bitcoin instead of into dollars? These are complicated questions, a bunch of which have to do with the way that this pandemic gets unwound and so on, and exactly what decisions made by central banks and all those kinds of things. Again, one could talk about this. I'm not sure this is quite the right venue for that. But what happens is there are always new ideas for how to make cryptocurrencies. So for example, this idea of proof of work, this crazy computational irreducibility idea, there are other approaches. Proof of stake is another idea, where you basically have a sort of pseudo-democracy where people, based on how much of the cryptocurrency they own, they get to kind of vote on whether they think that this block is correct to add to the blockchain, things like that. So there are a bunch of ideas like that. There are ideas where people have sort of variable possibilities for how the thing gets structured, and people can kind of like change the constitution, so to speak, by an appropriate kind of vote of people who own that cryptocurrency, those kinds of things. There are lots of different governance mechanisms. And in general with cryptocurrency, one of the big sort of interesting things is the way that you create these incentives. Like, oh, nobody wants to fake this because if they fake it, then this will be bad, and it has value to do the correct thing, et cetera, et cetera, et cetera. So we've worked a bunch on this, and actually the thing that I think is the most interesting, ultimately, a couple of things with cryptocurrencies. So one thing is usually with real money, it has value because it is a medium that's dealing with actual economic activity, actually people making things and selling things to people and doing services and charging people for those services and so on. That's what that's what economies are really based on. And the currency, the dollars that get exchanged, are really just a reflection of people sort of using some medium to pay each other for those kinds of real economic things that are happening. So there aren't really real economic things that are happening mostly in cryptocurrencies. And that's a problem because it means there isn't the same stability. There isn't that same level of real things that are backing the sort of the value of the cryptocurrency. But something which I think is a coming sort of thing is what I like to call computational contracts. When people write legal contracts, they say, you know, I'm going to do this. If this happens, you'll pay me this. If that happens, this will happen, et cetera, et cetera, et cetera. Those contracts today are pretty much written down in English words or in words of some language. They'll say, you know, whereas the party of the first part does this and blah, 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 blah in legalese, but it's basically something that just sort of says in words what's going to happen. So the question is, can you make that into something which says, instead of in words, in code, in some kind of computational language, what's going to happen? Well, for that, you have to have that computational language be enough connected to the real world that it knows whether the thing happened or not, that it knows, you know, it's connected to some camera, it's connected to something, some bank balance somewhere, it's connected to some other thing in the world where it can say, those were the provisions of the contract, did you actually do them? Oh, it can know whether you did them. And then the actual sort of content of the contract can be represented in this computational language. And then you can it can decide, a computer can decide, was this contract followed? And oh yes, you know, so-and-so gets to pay so-and-so such and such an amount of money, or not, as the case may be. So this idea of computational contracts, it's sort of, they've happened in a few areas. They're gradually expanding. Our kind of Wolfram language, computational language, is, I think, the most suitable for actually creating broad computational contracts. And so it's part of the reason we've been sort of involved in the world of blockchain, is because computational contracts are something which, when they are widely used, will be a thing where computers interact with computers and a lot of sort of contractual activity is happening autonomously. So right now, contracts are like, a human says, you're supposed to do this. Somebody says, oh yeah, okay, I'm supposed to do that. And if everything blows up, you take it to court and some judge decides or some jury decides, did you do what you were supposed to do? But in the future, one can expect that those are computational contracts and they're purely decided by what the computational language says should happen, and they can be decided by computer. And that means you can have these giant chains of contracts where if something happens, that causes the triggering of a whole chain of contracts, all autonomously, all just happening without human intervention. Things could go horribly wrong in that setup, but you know, if you get it right, then it's a very efficient way to operate many kinds of things. So in that situation, some number of contracts of that kind will probably want to use cryptocurrency as the medium that they're exchanging, because it's convenient to do that. If the contract is for a small enough amount of money, probably nobody cares about having sort of the transparency of cryptocurrency. If it's a really huge amount of money, probably people want the security of being able to say, if something goes horribly wrong, I can take it to court and there will be some chain of humans who decide what to do. But there's an intermediate range where probably cryptocurrency is pretty good. But computational contracts don't exist yet. Well, they exist, but they're not very widely used. I mean, there'll be a time when trillions of dollars of value is exchanged all the time in computational contracts. And when that happens, there will be sort of real economic activity on top of which you can build the value of a cryptocurrency. But so that hasn't quite happened yet. And I don't think that will happen the next year. It will gradually happen over the course of quite a few years. The other thing in the world of cryptocurrencies, actually, we recently had an idea that sort of comes out of the physics project. And here's one of the big problems of cryptocurrencies. You know, with Bitcoin, I mentioned you're putting in these blocks, which are on the blockchain, which are, you know, this ledger of all the transactions. But the time between each block is about 10 minutes. And the time before you absolutely know that this was a really secure transaction might be as long as a day. And so that's very, very slow. So if you want to be exchanging money with people and so on, you want to do it reasonably fast, it's too slow. And also the amount that you have to pay to sort of justify having the, I don't know what it is, 5,000 people who have a copy of the Bitcoin blockchain on their computers, to justify sort of having that be kept on all those computers, it's a fair amount of money. So it's expensive to do transactions and it's slow to do transactions. And so there's a question of, is there a much better way to do it? And what we realized through our physics project is that there is actually a much better way. It looks like there's a much better way that very amusingly uses a bunch of ideas from quantum mechanics and so on, that the way that that works in our physics project to be able to make a much faster version of something like a cryptocurrency, except it'll have weird features. Like, for example, it'll be the case that if you don't care, if you allow your bank balance to vary by, let's say, 1%, you can find out what the value should be very, very quickly. But if you insist on it being absolutely precise, you might have to wait longer. And it's kind of like the uncertainty principle in quantum mechanics. And it actually happens for exactly the same reason in the system that we're imagining. And so one thing to me that's interesting about this potential sort of blockchain, is more general than cryptocurrency, is that it's actually very much based on the ideas of quantum mechanics, which is this thing that people don't have good intuition about. And I think one of the things for me that's kind of at least amusing is that if in fact it becomes the case that people often do transactions using this kind of blockchain, then people will start to have an intuition about quantum-like phenomena because they will be experiencing it every day in the way that those transactions happen. So that's one of another sort of coming attraction. No, I don't know. I can't tell you a prediction for whether, Cardano or Tezos or Ripple or this or that or the other is going to go up or down in the near future. Oh my gosh, so many questions. There's a question here about Bitcoin and cryptocurrencies. Are big banks and governments trying to undermine the legitimacy of cryptocurrencies? I don't think that cryptocurrencies are particularly favored by governments, because in a sense, a cryptocurrency is just this thing sort of operated by this mysterious network of computers, supposedly without human intervention. And kind of governments are in the business of running how the world works. And we've discovered in this pandemic, for example, even if you thought governments didn't matter, turns out when you have a big public health disaster like this, you have governments do matter. Somebody has to centrally say, oh, you've got to do this or that or the other. And that's, government, and it matters whether the government makes the right decision, the wrong decision, et cetera, et cetera, et cetera. That kind of centralization to a government does seem to matter. I mean, people have often gotten to the point of view, I have to say, I sometimes think that the less government, the better, so to speak, and the less one has to sort of interfere with things, the better. But it's kind of like somebody has to decide, do you drive on the right or left-hand side of the road? That has to be a centrally made decision. Well, another kind of decision that seems to be necessary to make centrally is things about the amount of money, the number of dollars you print, the money supply, the rate at which the government will lend out money to people, T-bills, things like this. Those are the things which sort of have to be centrally decided by the government. And governments feel that by making those central decisions, they get to, control what's happening. Some people may say they're controlling it for good. Some people may say they're controlling it for bad. It does, that's a thing. But the government at least thinks they have levers that they can pull that will make things happen. Like if it turned out that, the economy in some country was just grinding to a halt, or the currency was, dramatically inflating over time, the governments think that they have levers they can pull that will sort of control what's happening. So if it starts to be the case that a lot of the economic value of the country is in cryptocurrencies, that gets very scary for governments because those levers just don't work. They're not attached to anything. Now, it's also the case in many countries where there is a so-called informal economy. In other words, where people are just paying each other either in currency or by barter, and they're not reporting that to the government. And they're usually not reporting it because they don't want to pay the tax which the government will levy on those transactions. And so sometimes it's hard for a government to know, it's hard to control that because it's like, well, you can try and enforce, nobody can do those transactions, but that's about all you can do. You don't know what's happening. You can't pull the standard levers to change the way the economy works if most of the economy is operating in a way that doesn't depend on the government. So I think governments generally are not, it's like, in many cases, it's like it'd be better if cryptocurrencies just went away. And it's very complicated to know, for example, how tax should work on cryptocurrencies. I mean, I think that And it's also people worry about, I was very amused a year or two ago now. People worry a lot about scams with cryptocurrencies. It's very easy for somebody to put up a website and say, I'm creating a cryptocurrency, invest in my cryptocurrency. I'm going to do amazing things. It's just complete nonsense, right? And it's kind of amusing because I guess it was the SEC, Securities and Exchange Commission in the US, put up a website for a fake cryptocurrency. And basically, you clicked on this thing, and it was really funny, actually. It had pictures of people sort of reclining in the sun on a beach somewhere. Of be that you get to be this if you invest in our cryptocurrency and so on. It was quite over the top, actually. It was quite amusing, but it was a fake. And if you clicked on any of the buttons, it would say basically, this is you could have been had. If this wasn't a government site, this could have been a scam, and somebody could have been taking your money and doing nothing useful with it, and just spending it on themselves and not giving you anything of value back. So the fact that it got to the point where the U.S. government was running kind of a fake scam site meant that I thought that was a strange moment, actually, for the web and for the way that things work, and for the sort of don't trust everything you see on the web. Even the government is running fake sites, so to speak. So in any case, it was a concern. It is a concern that people will just get that it's in sort of an area where there's a lot of kind of people can say, I put up a website, I'm going to take in your money, it's all nonsense, and then people will get upset. But that's a kind of a separate thing from a government getting upset, because it's like we've lost control. Everybody in our country is all their money is in Bitcoin, and we can't control that, so to speak. And sometimes countries get to the point where they're very worried about their currency leaving the country, because it becomes harder to sort of keep value in the country, and then they try and put exchange controls on their currency and so on. And that's happened with, I don't keep track of which exact countries have done that at this moment in time. But there are plenty of countries in the world right now where there are exchange controls. And if the money is in Bitcoin, it's like, sorry, you don't get to do that, because Bitcoin is this global international thing that's just based on a network of computers. You don't get to tell people, oh, sorry, you can't take your money that was in such and such a currency out of the country. So yes, I think it's not, it's kind of an alternative. It's a way of potentially making something that is sort of transcends the what governments provide. Unfortunately, it doesn't really work, because the truth is that people tried to actually make a sort of a purely autonomous system where it would sort of develop value and be something that was purely under sort of computer control. I'll tell you what happened to it. It was an interesting story. It was a thing called the DAO, the Distributed Autonomous Organization. And it was essentially an investment vehicle on Ethereum. And the idea was people invest money in this thing and it gets spent on useful projects, and you get paid back based on those useful projects, and it's all a good thing. Okay, so fine idea. Problem was that the website proudly said there are no humans involved in running this. This is just being run with computer code and with essentially computational contracts. Okay, well, somebody found a bug in those computational contracts, and that bug allowed them to transfer $50 million to themselves. Okay, so they did. And then they said, so then the question is, was that actually against any rules? And it's like, this whole thing said on its website, everything is run with code. It's just code. The code defines the law here. Okay, so this person said, well, the code defines the law. I found what many people would say was a bug, because it wasn't intended that somebody just be able to transfer $50 million to themselves. It was intended that this money would get used for venture capital, for projects and so on. But it didn't actually, it said all over the place, this is all governed by code. There's no, by computer code. There's nothing other than that. So it's even a question whether there was sort of really anything wrong with the person saying, well, I'm just following the code, but I transfer $50 million to myself. And so people were like, well, that was the wrong thing to do. That was very, very shocking. But unfortunately, there was no direct recourse, because there wasn't like you could say, you did the wrong thing. You broke this contract. Look, I can waive the piece of paper. I'll take you to court. I'll get a government to enforce the fact that you got to follow the law, because there wasn't any government involved. It was all just computer code. Okay, so you might wonder what actually happened. So the big question was, would the sort of majority of people decide that they would just ignore the code that this person had run and change this ledger, change the blockchain, and just go back and say, reverse out that transaction. We'll pretend that transaction didn't happen. Even though they'd ratified the transaction, just say, we're going to fork this blockchain. We're going to have two copies, one in which the transaction didn't happen, one in which it did happen. Or just say, we're going to reverse out that transaction. We're going to change this blockchain. So what happened is there were two forks, one in which it got changed, one in which it didn't. So there was some set of people who said, we're going to just follow the computational law, and we're going to just say, this person could do this. That was what the code said. Let them do it. And the other group said, no, we're going to take some sort of overarching human control of this, and we're going to say we're going to back out that transaction. So I haven't looked recently, but last time I looked, the one where people had backed out the transaction was worth 10 times more than the one where they hadn't. And so that was kind of a lesson of, at some level, it's actually a good idea to have humans in the loop. And that's really the question of whether, that's sort of a proof of the value of governments or something in that case. Now, you can say the government's going to do the wrong thing. I don't like that government. One of the things about the world today is there are a couple of hundred countries in the world. It's not the case that there's just one government. I mean, to me, if you have just one government and it's going to be the perfect government, it's going to do exactly the right thing under all circumstances. What that means, who knows? Because it's always going to be the case that there's, the government's going to do the perfect thing, but it's not going to be the perfect thing for everybody. It might be the perfect thing for 90% of the population, but 10% is very unhappy. It might be the perfect thing for 51% of the population, but 49% is very unhappy. It's not really possible to solve that problem. That's kind of the fundamental problem of political philosophy or something, is that you can't, if you are having these central decisions, you can't make decisions which are going to make everybody happy all of the time. And so, the thing that's happened in the world, among other things, is we have a couple of hundred countries. And so that at least gives, even though there's not complete flexibility to move from one country to another or whatever, that at least gives some possibility of the world not being this very fragile place where it's kind of like, there's just one thing. If we make a mistake, if we, if there's a bug in our computational constitution that determines how our one world, country works, then everything's toast. The world isn't set up that way, and it's probably for the better. Now, the question of why there are 200 countries, can we explain why there are 200 countries rather than 1,000 countries, or rather than 18 countries? I don't think that's easy to explain. I think in the past, one could have said it's sort of geographical. Countries are, based on actual borders, and to some extent that's still true. But there's also a question of, why do countries not fragment into smaller pieces? There's some value to having a bigger country. There's some value to having, to having everybody who is kind of really likes this thing make their own country and make it separate from some other country. And that's, a complicated thing that happens in the world that you can kind of look with. We have the data of language of sort of all the historical country borders throughout recorded time. There are about 4,000 sort of distinct country-like things that have existed in the course of human history that we know about. And you can kind of see, you can make an animation of how those country borders move over the course of time. It's kind of shocking, because it looks so much like some kind of process that's happening in physics or biology or something like that. Things will get bigger and they'll split, and then something will get really, really big, some giant empire, and then pop, suddenly it disappears and there's none of it anymore. And it looks like a very kind of physical process. It doesn't look like a process where on the ground that was humans doing, huge amounts of effort and having wars and fighting and agreeing on things and so on and so on and so on. It just looks like some physical process that could be taking place with a bunch of microorganisms or things in just purely in physics. So it's kind of a weird thing, but that's and I don't really know how to think about sort of this process of countries breaking apart, countries, combining together the different forces that cause those different things to happen. it would be quite interesting if there was sort of a way to say, oh, if there are 7 billion people, there are going to be 200 countries. You might have thought, given that there are a lot more people in the world today, that there would be more countries in the world today than there were in the past. There are actually probably slightly fewer than there were in the past. And that's probably a trade-off between number of people, mechanisms of communication, the kind of cost of having a country. You know, if you have a country, well, you have to have your postal service work. You have to agree on, you know, what's going to happen with your satellite, you know, with your internet fiber optic cables. You know, there's a certain sort of set of infrastructure that you need to agree on to sort of have to stand up a country. You know, you have to say, we're going to be members of this treaty and that treaty and so on. So I think it becomes, it's probably a little bit more difficult to kind of stand up your own country at this point than it was in the past. But you know, I think that's a, but you know, the question was, is it sort of cryptocurrencies against the government? Well, I think to some extent it is, and I think this is one of these things that's complicated because it's, you know, it's part of the sort of trade-off of, you know, if a government tries to say we're really in control, we're going to control everything, people get upset and say we don't want that, and then they sort of push back and say we're going to invent these things that sort of go around the government. If the government is like, oh, we're not doing anything, we're just hands off, and then, you know, terrible things happen and people say, hey, government, you should have been, you know, paying attention to this, doing something about this. You know, you should have been going and making sure that other country didn't you know, attack us or whatever. You should be making sure that this or that thing, you know, happens. And then people say, we want the government to do more stuff. And then, so it's, you know, it's a complicated trade-off, which I don't think ends in any particularly clear way. I think the thing that is interesting to think about now, and maybe this is a complicated topic for this venue, but is given that we have kind of the idea of computation, how can we change sort of the processes of government? And you know, the fact that we could have democracies that work with people having votes and putting them on pieces of paper or however they do them, and you know, that depends on, for example, the fact that people can you know, get to a place to vote, that you can move the votes to a central place, that you can combine them, that people can read at least enough or can be literate at least enough to have some idea what they're voting for and be able to, you know, fill things out and so on. And the question is, if we have a world where everything is computational and where even people are computationally literate, how does that change what's conceivable in terms of the management of the world, so to speak? You know, right now, democracy is sort of somewhat enabled by communication, literacy, things like that. What is enabled by kind of computational literacy? What is enabled by the things that we can do computationally today? And I've thought a bit about this, and there are certainly things one can imagine as kind of thought experiments, some of which don't end well. I mean, one is, instead of saying, I vote for A, B, and C, you say, I'm going to write a computational essay which defines in computational language what I want to be true about the world. And then you take, you know, 100 million of those things or 1 million of those things, you combine them all together, and then you have this big AI program that says, given all these things that all these different people want, here's the way to best achieve whatever best achieve means, the things that people say in their computational essays. Unfortunately, to do that, you run into exactly the same problems of political philosophy that you run into in all these other places, where it's like, well, what are you really trying to achieve? Is it like 90% are happy, even if 10% are very unhappy? What are you trying to achieve? How do you kind of make that landscape of who's happy, who's not happy, based on these complicated computational essays? But you get a lot more sort of fine control of things by doing that than you do by just saying, I elect so-and-so to go represent me. Another thing that's true is that in sort of this world, you can imagine something where you would even say, so the feedback mechanism, oh gosh, you know, you voted for this, you put this in your computational essay, whatever, you know, you can get an alert on your phone that says, this thing just happened in the world that can be traced back as a consequence of this thing that you voted about 2 years ago. And so that's something we don't have right now. I mean, people just say, I vote for this. Okay, so-and-so, you know, I get this person as you know, in this political position. And then it's like, okay, and they do what they do, and you know, things happen, but there's very little feedback, you know, until the next election comes up and people say, oh, that person did a terrible job, oh, that person did a great job, whatever it is. It's, you know, it'd be kind of interesting if you could see on a more microscopic level, oh, you know, this thing just happened in the world, and that was a consequence of the thing that I voted for, you know, 2 years ago, and so on. And that would give people a kind of feedback they don't have right now. Now, whether that's, many people would just say, I don't care, I don't want to be, I'm not in the business of running the country, I'm just doing my thing. Let's let somebody else go run the country. I think but there are things one can imagine doing, and I certainly haven't figured them all out. I've been sort of meaning to think about this at some point, of sort of the computational democracy, so to speak. What does it look like? What are the new possibilities for sort of the governance of a country that are made possible by the existence of sort of computation and computational contracts, computational essays, those kinds of things. Oh boy, there's specific questions about what do I think about China's digital currency. It's always interesting. Parmenides asks, is that what caused the Ethereum hard fork? Yes, the answer is yes. It's always very complicated to, I don't know, I probably will get myself too deep into politics to talk about, which I don't want to do, to talk about kind of the relationship between sort of what people actually do, what people say they're going to do, what it's a funny thing, because we as a species, so to speak, we respond a lot to stories that get told. The narratives, the kind of the marketing message about what's going on is often very important to what people decide to do. And even people will say that was the right thing, even though something very bad happened, if the marketing message was right. So it gets really complicated to disentangle kind of what is, what's the message versus what's reality versus what was the consequence of this versus could anybody have known what the consequence was going to be? Can you blame somebody for that because they knew what the consequence was going to be, and so on? And I think that one of the things that tends to happen is there's sort of often a trade-off of, do you want the government to be like doing a lot of stuff, or do you want them to just be like, just try and keep everything running smoothly and don't interfere too much? And then it's kind of like, well, something's wrong with society, so therefore we have to move some lever to try and make it go in a different direction. Well, sometimes it's very hard to predict what moving that lever is actually going to do. And sometimes the consequence will be some disastrous thing in some direction, which was very, very hard to foresee. And sometimes the kind of, a lot of ethical questions end up with, well, there's a lever you can see and there's a consequence you can't see. And people tend to pick, let's, even though we have certain chances that things we can't see will be disastrous, we'll pick doing the thing we can see because that seems like the right thing to do, even though at a sort of deeper rational level, you can kind of see it's probably not the right thing to do. So there are lots of kinds of complexity there, which I certainly wouldn't claim to understand. I mean, I think the only thing that I think I do have some understanding of is this phenomenon that, people sometimes have said, look, we can just, if we have enough science, we can make a perfect government. We can just make everything run perfectly. We just use science and everything will work. We can calculate everything. We can calculate how the economy should work. We can calculate how, all these different systems should work, and we just use science and all will be well. Well, the thing that that's a phenomenon that's sort of grown over the last 500 years or so, of the just use science phenomenon. And I think that that mechanism of so one of the things that I've realized as a result of science I've done is that there's this phenomenon of computational irreducibility. Even though the scientific rules by which something may work at a small scale, you can't predict what the many iterations of that rule will do. And that's a phenomenon that is not to do with us being kind of, stupider than we should be, so to speak. It's a fundamental phenomenon about the way that science and mathematics work. But there is this phenomenon of computational irreducibility that even when you know the underlying rules, you can't foresee the outcome sort of more efficiently than just running the system to see what it does. And so that's a case in which sort of science is showing its limitations from inside science. That's not something coming from outside science and saying, oh, science is all nonsense. We really know what's true from some other kind of, spiritual belief type thing or some other thing. It's not something like that. It's simply saying that from within science, we know there are limitations to science. And so from that point of view, one can kind of realize that these things where people say, we'll just use science to decide what to do. Well, that's just not going to work. In the end, there's going to be what we would call a judgment call. It's going to be something where we can't know what's going to happen. We just have to say, we're going to do this, even though it might be wrong, because you got to decide something, and it's sort of a judgment call. You can say, well, I'm going to weigh these factors and these factors, but you'll never get it perfectly right. And however good the science is, it's never going to be able to decide the answer. So it's not, we can't just say, let's abdicate human responsibility and just say, let the science decide, because it can't. It's limited from within itself about what it can say. And I think that's an important thing to realize, which, I don't know, I've been talking about computational irreducibility for about, what is it now, 35 years or so. And there's a slow, in some areas of science, it's decently well understood at this point. But I think in the world at large, it's only slowly beginning to be understood. And people are still on this idea that kind of started 500 years ago with folks like Copernicus and so on, that it's kind of like, we've got science, it's going to solve everything for us. Don't worry, if the scientists get far enough, they will be able to solve everything. It's just not going to happen that way. It cannot happen that way. It is a fundamental feature of the structure of science itself that it has those limitations. And it's not a phenomenon of our inadequacy with our brains, our computers, anything else. It's just a consequence of, well, it's really a consequence of this thing I call the principle of computational equivalence. It's a consequence of the fact that our brains are no more computationally able than these systems we're studying. And so that means that we're never going to be able to sort of outrun those systems. So that's a place where sort of can we make a perfect government or something? The answer is no, just as we can't make sort of a perfect legal system which has no weird sort of cases that sort of have to be decided by judgment, so to speak. So I think that's somebody's commenting, Dr. Doom, good name for this comment. The concept of a democracy AI makes for a great science fiction novel, but horrifying when applied to real life. Well, yes. I mean, it's a complicated thing, because there are features where people will say, oh, it's fairer to have an algorithm just decide. Yeah, I mean, to some extent, but it's, in the end, there is no right answer. So the algorithm will implement some answer that it is basically, it'll implement certain kinds of constraints. It will have features that you can't readily predict, but you can implement certain kinds of things. It's something where, in the end, it's the giant AI that just decides what to do for the good of everybody. It's not a possible thing. Anyway, let me see. So, gosh, that was a long answer to that. There are a few other questions here. Boy, there's a question from Abteilung something. Is finding the shortest proof of a theorem computationally irreducible? Yes, that's an example of something that has this phenomenon. It's a sort of classic example, actually, of that feature. Let's see. Boy, there are a lot of interesting questions here. Wow. Let's see. There's a question here from, I think, Nick. If you were sent into the past with one object of your choice with no return, what would you do to speed up human progress? It has to be a computer. That's I think, a computer with all of the knowledge that we have on a modern computer. That's almost cheating, because it's almost like saying I'm taking a software version of all of modern technology. Now, how I get to power my computer, that's an interesting question. I think I'd have to have some kind of solar thing or something that I can hand crank or some such other thing. I mean, I've sometimes thought it's sort of a fun question. If you took a computer, take your laptop and you show it, you take it back a few hundred years and you show it to people and you say, you wonder what on earth do they think this thing actually is? I was thinking one day, I've been thinking about this for decades, and it's one of these things I should eventually get around to, just for fun, writing a little book of kind of fictional dialogues with sort of thinkers of the past, which kind of launched by, I've got a laptop, here it is. And they're like, what is this thing? And it's like, you could imagine Pythagoras, 500 BC roughly. Pythagoras looking at this laptop, what the heck is it? It's doing all these things. I think that probably his view would be that the laptop is some kind of disembodied human souls. It's kind of like all this stuff is happening. Somehow in this box, you have disembodied human souls. Now, what's interesting about that point of view, and I'm sort of just back projecting by 2,500 years, so who knows whether that's actually what would be concluded, but it's kind of like, is that a reasonable model for what's going on? And then you might ask, well, whose human souls are they? Souls are associated with a person. These disembodied instances of sort of things happening, of thought. They must be associated with a person. Whose are they? Well, there are programmers. There are people who created, this computational knowledge, et cetera, et cetera, et cetera. In a sense, this is a repository of some version, some sort of shadow of their kind of soul, so to speak. And that's one point of view. But it's kind of interesting to see at different times in history, what would people think? What would Newton think a modern laptop was? Some kind of weird chemical process type thing of perhaps of producing, all these chemical things, some kind of alchemical thing. I'm not sure. It's interesting to see what will be the kind of cognitive model of what's happening in a modern sort of, in a modern laptop, so to speak. And then how would that, given that, what is the actual mechanism by which you generate, what would accelerate human progress? What artifact from today would have accelerated human progress in the past? And then, I view my personal activity in some sense is creating artifacts from the future and delivering them today. So it's kind of like when we build out this, computational language or something, we're creating things which I kind of think, rather perhaps arrogantly, that, if left to its own devices, the world might invent these things in 100 years. And, my personal sort of, feeling importantness comes from the fact that maybe I can bring those things that would have naturally been invented 100 years from now and invent them now, and deliver them to the world now. But there's sort of a big question of if you have an artifact from the future, and this question posed if you could take something from today and take it back to some number of hundreds of years in the past, what given that you have an artifact from the future, how would you use that to change the world, so to speak? How would you use that to pull the world towards that future? If that's, it's not the case that at every time in history, people have actually been interested in being pulled towards the future. I mean, today we still have the point of view that the future is good. I'm not sure that people always have had that point of view. Sometimes people have had the point of view the past was good. I mean, for what, 1,500 years, people were using the infrastructure that was built by the Roman Empire. And it looked like the past was pretty good. We don't know how to build all these fancy stone buildings and aqueducts and all those kinds of things. We don't have the organization to build them today. So it looked like things were really pretty good in the past, and it's not clear the future is better. But in today's world, we have the point of view, the future looks pretty bright. And so from that point of view, it's like, okay, you're put back in some time in history, you got your laptop, it's got all kinds of information on it. What do you do? And how do you actually, what is the mechanism of taking that sort of knowledge and that spot of knowledge, so to speak, and diffusing it in the world? I have to admit that's a little bit the problem I sometimes feel in some of the things that we do when we build technology. When technology I built, for example, it's like we built this great technology, and now we have to diffuse it out into the world. We have to essentially get the world to know what we've done and sort of absorb it. And same is true with scientific ideas. It's often not very easy to do that. It's often a very complicated, long, arduous process to do that. And sometimes it's something where it's not the work of one person to do that, because it's something that ultimately has to be diffused across kind of the knowledge and beliefs of a large number of people. So it's kind of a challenging thing. It's kind of almost like you go back in history with one technological artifact, and it's like you have to start a whole giant movement. You have to become, a political leader or something to be able to get anything to happen with that amazing technological artifact that you've delivered back into the, from the future, that you've delivered into the past. So I guess as I think about it, I'm a little bit pessimistic of, one person, one laptop or whatever. What would you get to show from that? And it's kind of like, well, you could imagine, you say, well, let's take back a rocket or something, or let's take back a fancy airplane. Of course, you have to have the infrastructure to operate the thing. But even if you could do that, so what? I mean, you've got a big airplane and people say, well, we can see birds. And what is this thing? That's a really weird thing. Who cares? And then maybe you start the giant cult of the airplane. But that's then a complicated human organization thing that has little to do with the piece of technology that you brought back. I mean, maybe you get to sort of act like something that is it's kind of like this is the amazing super wizard human type thing, and everybody should pay attention to them because they have this piece of technology. Look, they have this piece of technology, therefore, but it becomes a very different problem. It becomes can you lead the people to do something reasonable rather than you have this piece of technology? Now, obviously, there are things where, for example, to build a laptop, there's a huge layer of infrastructure of, you have to have the precision manufacturing, the, creating the crystalline silicon to make the chip, creating all of these, having all this infrastructure of mining different materials to use for this and that and the other, setting up all this kind of precise machinery, which was built from many generations of other precise machinery and so on. There's a huge amount of infrastructure necessary to create a laptop. And if you bring back a laptop, you don't get to bring back the infrastructure to create laptops. I mean, perhaps sometime in the future, we will have closer to self-replicating machines where it will be enough to just bring back one of those machines. Just like, we have very good in living systems, we have that. They've solved the problem of making a molecular scale thing that replicates itself. We haven't solved that for technology. We can't do that kind of on demand for technology. So I don't have a great answer. This is a really interesting question. All right, let's see. There's a question from Kelly asking about genetic reprogramming to reverse aging, and what am I doing, because I'm an ancient character by now, to extend my life? So far, not a hell of a lot. I pay a lot of attention, I've paid attention for decades to those kinds of things, but really it's just like do the obvious things and don't, I haven't figured out or become convinced enough to see, some particular, obscure kind of take this chemical to live longer type thing. There's a question from Icy here. Do I have a spiky, one of our Wolfram Spikies on top of our Christmas tree? We've often had that. I have not noticed, I have to admit, this year. I would say the likelihood is high. They're very convenient Christmas tree toppings because they're cardboard. You assemble them. They assemble in 12 panels, and if you leave out one of the panels, you can stick the top of the Christmas tree through that. So that works well. All right, maybe one or two more questions here, and then we should wrap up. Let's see. It's a question from Parmenides. Do I know any of the people involved in designing the Ada programming language? I don't believe that I did. There was an attempt. So there are different kinds of programming languages. And there was an attempt in the early 1980s by the US Department of Defense to create a standard programming language that everybody would use. Unfortunately, as is often the case, when there's a committee designing something, it got very, 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 very complicated. It got so complicated, I'm not sure it was ever even implemented. I think it's one of the languages that was designed by a committee. Very few of the languages, in fact, I can't think of any language that became popular that was designed by a committee. There was another one from much earlier in the history of computing, Algol, in the early 60s, which was also designed by committee, also got kind of complicated, also was never implemented. Had a bunch of ideas that were used for other languages, but it was never fully implemented. I believe Ada had the same situation. I don't think it was fully implemented. And I think what ended up happening was one of these things that's sort of terrible about the way that people set up rules and then people figure out how to game those rules is, the Department of Defense said, all our code has to be written in Ada. And then people started writing converters that would convert from C and Fortran and so on to Ada. And of course, the code that they produced when it was automatically converted from this to that was absolutely horrible code that nobody could possibly read. So the idea of having this Ada language was everybody will make a common language that everybody can read. The actuality was most of the Ada code, insofar as there was any Ada code that was created automatically from other languages and almost completely unreadable. So it was not a successful idea. Let's see. Parmenides is commenting on my comments from about Pythagoras. Just tell Pythagoras that the computer just runs completely on numbers, then he would be very happy. Well, that's not a bad strategy. I think what to me would be a satisfactory explanation of how something works is very different from what would be a satisfactory explanation to Pythagoras. I mean, if you look at what Pythagoras talked about, it's things like he had a very definite kind of social meaning for different numbers, like a 1 meant, I don't remember what 1 meant, but there was a number for I don't know, men versus women versus happiness versus unhappiness. I don't really remember, and he was very, very amazed by this thing, the tetractys, the fact that 1 + 2 + 3 + 4, am I getting this wrong? Yeah, equals 10. He was very, very keen on that fact, and it's like. Today we're like, who cares? That's just a random fact about numbers. But he thought that was very significant. And so some of the things that he would think of as an explanation are just utterly different from what we would think of as an explanation. So it's a fair point. I mean, you might just say the computer runs with numbers, and that might be, okay, great, now I understand how it works. Even though to us today, that would be a quite inadequate explanation for most purposes. I mean, it's an interesting question. If you look at young kids, for example, and you say, what counts as an adequate explanation of something? And it's sort of an interesting question. As you go through different sort of stages of things at what point do you ask for what level of explanation? And, at what point do people in general just sort of say, well, why does this happen? I don't know, maybe it's a medical thing or whatever. Why does this happen? Well, we can drill a couple of levels down and this is why, and then we don't know any further. But some people will be quite happy with, well, we drilled a couple of levels down, so now we know why, even though there's still a big piece of sort of bedrock there that you don't know why that's the case. And I suppose in my own efforts to sort of find a fundamental theory of physics, we're kind of trying to go all the way. We're trying to say, let's see if we can get all the way down to the sort of ultimate machine code of the universe to understand sort of, in some sense, what's happening, even if we can't necessarily, because of computational irreducibility, we can't make all the connections all the way up to things we say today. Well, let's see, maybe one more here. Let's see, there's a question from Mikhail about formal proofs about computational irreducibility. That's a complicated story. There are particular cases in which one can give formal proofs, but the general concept is more general than any of those proofs. And it's the same kind of thing as the concept of, for example, heat in thermodynamics has the same feature. When you try and nail it down, you can nail down certain aspects of it, but there always will be things where there's a useful intuitive notion, which is a bit bigger than the things that you can fully nail down. And it's the same thing with computational irreducibility. As a guide to intuition, it's a bit bigger than any of the sort of specific slices of it that you can nail down, but you can nail down specific slices and quite big ones. Let's see. Oh boy, there's a question here. All right, let's two more and then we wrap for today. Question here from Saku Ashiba. Is it possible to make a wire from space to Earth and pull things up to space? You know, this has been a long-running question that people, it's often called the space elevator idea. You know, you have a satellite. Okay, first point is, you have a satellite that's orbiting the Earth. If you're in low Earth orbit, you go around the Earth every 90 minutes. So if you have a satellite orbiting the Earth and it's going around every 90 minutes, if you've got a wire connecting the satellite to the Earth, that wire is going to get awfully tangled up awfully quickly. But it is possible, if you go further away from the Earth, the time to go around one orbit gets longer. And about 24,000 miles above the equator of the Earth, you actually, it's a 24-hour orbital period. So that means that things that are orbiting, well, for example, above the equator, it doesn't matter where it is, but it's more useful above the equator. Things that are orbiting above the equator at 24,000 miles out will go around the Earth once every 24 hours. And that means that the Earth turns and the satellite moves, and it always stays at the same place relative to the Earth. So that's how, if you look at the positions of satellites in Earth orbit, there's a giant collection of satellites in geostationary orbit. In this orbit, 24,000 miles above the equator, there's a big sort of ring around the Earth. You might say, you know, oh, we have Saturn has a ring, you know, which is just little rocks and so on. The Earth has a ring too. It's made of satellites that are in that particular location above the Earth, which has the feature that if you're a satellite that's beaming television programs, for example, to, let's say, you know, North America, you can just sit at that one place above the equator, and as the Earth turns, you go around the Earth at the same speed that the Earth turns, and so you always stay above the same point in the equator. That's why, for example, if you have a satellite dish, that doesn't move, which most don't, then you'll point it in a direction that's looking 24,000 miles above the equator, looking, if you're in North America, towards the south, and it'll be pointing at a satellite that's sitting above the equator. So, okay, so you can have a geostationary satellite. So then you say, well, what if we just put a wire that connects the geostationary satellite to the Earth? You know, we just have this wire that connects the satellite to the Earth, and then maybe we just have something which crawls along the wire. It just has wheels or something, and it just runs itself along the wire to go from the surface of the Earth into orbit. Okay, can that work? Okay, big bug is there is no material strong enough to even maintain its own weight getting on that long a piece of wire. It's like having a suspension bridge, and the suspension bridge is 24,000 miles long. And there isn't a known material that is that strong. Now, there is some hope that things like carbon nanotubes, these kind of molecular scale materials made from the sort of new arrangement of carbon, might conceivably be knitted together to be strong enough to make a kind of a cable that could be 24,000 miles long and go from the surface of the Earth into geostationary orbit. And so that's the main issue, is you can't make something that's strong enough to have that, to create that kind of wire that you can then sort of crawl along. But it's not obvious that there can be no material strong enough. There's no sort of proof that it's not possible to make a material that's that strong. It's just a question of people finding a material that's that strong, and probably it will require creating a material sort of from scratch, you know, creating the atomic structure to make something that strong. We don't really know how to do it. I mean, there are a lot of funky ideas about how to get things into orbit. Another one that was popular for a while was you just shoot it from a big gun, so to speak, rather than having a rocket that has its own fuel, where the rocket fuel is causing gas to be ejected from the bottom of the rocket at very high speed and pushing the rocket forward. Instead, just have something where you have like a rail gun, where you have something where you have the thing in the gun, so to speak, and the either magnetic or chemical process is just making something go really, really fast in this gun, and then out into fast enough that, you know, like 17,000 miles an hour orbit insertion speed or whatever, and to sort of zoom out to orbit. I mean, there's another idea. There's a company actually that's trying to make something which just spins things around really, really, really fast, and then it spins them really fast, and then it just sort of opens a little door and lets the thing go, and it's spinning so fast that it just sort of goes fast enough to get into orbit. We'll see whether that works out. It's kind of an interesting thing, because if you're spinning something around, you can be spinning it around in a vacuum where there's no air resistance. And it's only when that little sort of door opens that you get, that you have to time things exactly right to get it to kind of exit the spinning area at the right moment to be able to get into orbit. We'll see. There's a question here from Trevoid. What will math look like in 1,000 years? It's a good question. I think the maybe I shouldn't address that here, but I've thought quite a bit about what the kind of limiting structure of mathematics is. In math, there are things we learn. We learn all kinds of facts about numbers. You know, we learn that the prime numbers have this particular pattern. We learn that this particular thing based on prime numbers and pairs of prime numbers and this and that and the other works in this particular way. We learn a series of facts in mathematics. And over the course of the last, many hundreds of years, we've learnt many different facts about mathematics. When people write them down, there are about 3 million kind of theorems that people write down about facts that are true about mathematics. People have written down in all the kind of research papers and books and so on about mathematics so far. But there are an infinite number of possible theorems about mathematics. But the real question is kind of not what theorems are possible. There's an infinite number, and we can have a computer just start enumerating them. But the question is, which ones do we humans actually care about? So, for example, it's just like saying we can go and look at all possible computations. We can go and look at all possible chemicals. We can go and look at lots of all possible things. But the question is, which chemicals, which computations, whatever, are relevant for us humans? We can imagine just an image, a picture. We can imagine a picture where every pixel of the picture is chosen at random. Is that picture useful? Probably not terribly useful. If it's a picture that's a wonderful picture of a cat or something, we say, oh, that's an interesting picture. But if we just pick those pixels by some other algorithm that makes the pixels look completely random to us, we just say who knows, that's just a bunch of random pixels. It doesn't seem significant to us. So the real question is not what is conceivable in terms of the theorems of mathematics. There's an infinite number of true theorems of mathematics. The question is, which theorems are ones that we humans are going to care about? And that's a more difficult question to answer. And I think that what we've seen happen in the history of mathematics, we've been steadily building out these kind of different paths where we build, and then we build more stuff on that path, and so on. And that's been what's been happening. And what's happened is often those paths that we build out, we get to a certain point and we realize, gosh, that's really, really useful for lots of things we want to do. Maybe we build technology that way. Maybe we build some cryptographic system that way. Maybe we build some other, compression algorithm that way. Maybe we do something else that way. So then a whole bunch of stuff in our world starts working according to that kind of mathematics. And then that becomes a big sort of area that we then build from and build on and build more stuff and so on. And so that seems to be a typical kind of thing that happens. And so if you ask what's mathematics going to look like in 1,000 years, it's, well, there's a lot of questions about sort of the future of our civilization and so on, and the future of sort of pure biological organisms versus computational kinds of things. Let's put those aside. Let's assume that we're just dealing with history that goes into the future, much as it's gone in the past, of just humans living out their generations in the way that they do. What happens to something like mathematics in that situation? And I think the answer is you build in all these different paths, and it's like the evolution of technology, human language, and so on. There are sort of new types of things that get created. What are the qualitatively different types of things? The major Cambrian explosions of technology, the sort of Cambrian explosions of mathematics, the times when just a huge amount gets discovered or invented in mathematics because of some new methodological idea. There are definitely ones of those in the future. I think we can see some already. I mean, I think I know a few that are sort of coming in the next few decades, perhaps. There are some, some to do with experimental mathematics, some to do with kind of a global theory of metamathematics, a global theory of the structure of all possible theorems. I have a bunch of ideas about using things that we've learned from our physics project to be able to sort of map out the geometry of the set of all possible theorems and how they connect to each other. It's kind of like, it's a trade-off between, it's like geometry and geography. Like we can know the shape of the structure of the surface of the Earth, it's roughly a sphere, that's of the geometry of the Earth. But there's the geography, which is, where do we actually choose to put our cities? Where do we actually populate on the Earth? And it's the same thing in mathematics. We can right now, we've been just sort of geographically populating different parts of mathematical space. But we can imagine also working out an overall theory for sort of the geometry, the analog of geometry for mathematical space. And I think I have some ideas about how to do that. And I think that will give us some clues about sort of what's conceivable in the infinite future of mathematics and so on. Just as we can say some things about what's conceivable about sort of the infinite future of where we can geographically populate on the Earth from knowing the geometry of the Earth. There's a question from Mark here. Tell a secret that huge tech company CEOs know that I was saying, since you're a tech company CEO, you might know something crazy in secret. I'm sure I do. And it wouldn't stay a secret if I were to tell it to you. But I tend to, because we've been a company that's been around a long time, and because I've known most of the leaders of a good fraction of what become large tech companies, I tend to know lots and lots of stuff about what people are thinking about and planning and so on. And part of the reason I know it is because I don't tell it to people. I think the thing, here's something which isn't a secret at all, but which people seem to think is a secret, which is, every piece of technology we have got invented by somebody. And people seem to have this idea that, it's this kind of, it sort of just happens. It's this sort of faceless thing where just somehow, big company X just makes a thing. Well, it's not that. It's actually, people, humans, somebody had to have that idea. Somebody had to invent the methods for doing it. And it's always quite interesting to trace through what actually did happen. How did that idea get invented? And for many ideas in the tech industry, I don't know whether many, yes, for many, I know the answer. I wouldn't say for most. The ones where I investigated. In fact, just last night, a friend of mine who's well-known person in computer graphics world, who's writing a book about history, sent me a link to some of the material in his book, which contains all kinds of information about early history of a bunch of computer graphics work, which is quite interesting and quite a lot, which I didn't know, and which makes certain things that happen make sense. But anyway, that's it seems like I misunderstood the question, and the question was about success in business and so on. I haven't been talking about business much in these live streams. Various people have suggested that I do some live streams about business, and I think probably the things I tend to know about, I've run a company for a third of a century now, and same company for a third of a century, and I've been involved in many other companies and so on, and I guess I've learned a certain amount about business. I think of myself as somebody who is mostly a person who figures out intellectual things. I've been competent enough at business to CEO a company for a long time and have the company be successful. And I think that there probably is there's a lot that I know about business that I think is kind of obvious. But it may not be as obvious to other people as it seems to me to be to me. And a lot of things about business have to do with, running businesses, taking advantage of opportunities, doing the right thing, not getting wound up in, There also, it's worth saying, there are different styles of running businesses. Like, for example, I tend to be, we're going to invent a bunch of interesting stuff. And that's the biggest priority, is invent the interesting stuff and do a good job doing it, rather than I'm going to listen to what all the customers say and I'm going to just follow what the customers say, even though I don't think the customers are saying very visionary things. They're just saying what the thing that they need to solve the problem that they have today, not thinking about the thing they'll need to solve the problem they have 10 years from now. But there are different styles of doing business. There are styles of doing business where one is really it's all about, persuading the customers to do something. There's styles of business where it's all about just making something great and explaining why it's great and hoping the customers will come and so on. There are lots of different styles of doing business. And, I've certainly, some of them I've followed myself, more of them I've observed in other people. Sometimes I've said, that's just not going to work. And often I'm right. It's just not going to work. And sometimes I'm wrong. Sometimes it's like, it's just a company like that just can't work. And then it becomes a multi-tens of billions of dollar company after a while. So sometimes one's wrong about those things. But and sometimes one says about people, that's a person who is definitely going to succeed, and they don't. And that's a person who doesn't have a hope, and they succeed. So it's always quite interesting and challenging. But yeah, I'd be happy to talk about that at some point. And I think there's been sort of various suggestions that I do a separate live stream about business and innovation. And I think we're probably going to try and start that in the new year. And that will be a good venue to ask lots of kinds of questions. And one of the things that's challenging about that is my first interpretation of this question about secrets. It's like I could tell you a lot of stories about our own company, about other companies, about our interactions with other companies, and so on. And at some point it becomes possible to tell those stories because so much time has passed that there's nothing sort of sensitive in those stories anymore. But it's sort of challenging to know at what point things pass into history, and at what point, oh, there was this person and they had this crazy idea, and then it turned out it was crazy, and they got this to happen and that to happen. And it's like, at what point does that count as being sort of just history? And at what point do you feel like those are stories that you shouldn't tell? And I don't completely know the answer to that. And that's one of the sort of challenges in these things. But anyway, so for another thing, probably for the new year, another set of live streams about kind of business and innovation and so on, probably aimed mostly at young entrepreneurs, and trying to pass on what wisdom I have, although with the important caveat that there are an infinite number of ways to succeed, probably like the theorems in mathematics, so to speak. And I can talk about ones that I've seen and ones that I've seen didn't work, but that doesn't mean that there aren't others that can work. All right, well, we should wrap it up here. And not sure if we're doing one of these next week. We might. Well, thanks for joining us, and see you another time.